let's take a moment to discuss the magnetic balance. So the purpose of this lab is to calculate the constant of attraction, the C star value, between two magnetic spheres, modeling them as ideal monopoles, Q star and Q star. We're assuming that Q stars are identical. This isn't exactly true. This is an analogy. Just an analogy. Something that we can try to kind of fit it to our understanding. It's not necessarily, well, it's not a real force law, but we're just seeing what would happen if we can make it look like one. So if we look at our analogy, we know that the electric force, the Coulomb force, is equal to whatever charge you have multiplied by the electric field that it's in. I guess force is a vector, and so is magnetic field. So our analogy says that Q star, the magnetic pole strength, times the magnetic field that this Q star is subjected into, gives you the force acted upon it, the force caused by this magnetic field. Our apparatus here this is a Helmholtz coil. You are going to run current through this Helmholtz coil, and it is going to create a magnetic field. The way these rings are set up, the field in the center is the same. It's a uniform magnetic field, which is very, very nice for what we're doing. A side note, you need to find this little r. Little r is the radius that this current is on. Oops, let's redraw that. All right. Then you are going to run a current through using this constant current source, using this little switch right here. And you'll go, and the higher the current, the stronger the magnetic field. A couple things to note, this high-low switch, if it is on low right now, you read the low scale. If it is on high, you read the high scale. Right? You're going to start with the writer far away. We'll talk about that in a moment. So you're going to want to start on the high scale and then work your way down. So the way this apparatus sets up, this is just a balance, right? We've got this little teeter-totter right thing. This is a writer. The thick wire is 1 gram. And then over here, inside here, you've got your magnetic field. B times whatever that other magnetic pole. And this distance right here is 10 centimeters, or 0.1 meters. Very important to use SI. So this 1 gram, make sure you convert it to kilograms. And then you know it's balanced when you're lined up and set directly in front of the center. If this is not balanced when the writer is on, these two little adjustment screws are used to make sure that it is zeroed when there's no magnetic field and no little mass sitting on it. So remembering back to first semester, when you have a teeter-totter, you balance the torques. We're going to assume that these angles are 90 degrees when this is balanced. So what we're looking at, if you remember, torque is force times radius times sine of theta, sine of 90 degrees just being 1, you would get your magnetic force times your distance r, the torque caused by that magnet, is equal to the torque caused by that little writer, mg, the force of gravity, times L. And you can solve this for the magnetic force is equal to mgl over r. Couple key points. This r is 0.1 meters, and it is constant. It is the distance from the center to the ball and the magnet. So let's take a look at this in action. You turn on the power supply, and you'll notice, look, slight turns cause this to go pretty fast. Now, you will balance this. I recommend always starting very far away because it is the least sensitive when the writer is very far out. As you get closer, it becomes harder and harder to balance. You will drive yourself crazy if you're not careful. So start with it really far. Just turn that knob right there until it's balanced. So a couple notes. Start with high L. Start with that writer as far from the center as possible. And then watch the high-low current scale. Make sure you're on the scale that you should be reading. Now there's a handy-dandy sheet provided, but please make sure that you make a table in your lab report. Do not hand in the sheet that we give you. This is just to make your life easier. It is a favor. All right. You read the current. You use this equation. N is the number of coils. All right, in one loop. Make that a little nicer. One loop. Gravity, force of gravity is just mg. And then this we got from that teeter-totter balancing the torques. And then using F magnetic equals Q star, our analogy that we're setting up, you get that your Q star is equal to F magnetic over B. And you'll get 9 values because you have 9 different L's. So the whole goal of this is to find Q star average, plus or minus. You will use this in part 2. All right, so part 1, you're finding the strength of the magnetic pole by balancing torques. So what we're doing now is we are going to look at this, and we need to find out, because in our Coulomb's law it relates to distance. We need to find the distance from this sphere to another sphere on top. So to do this, we need to figure out what happens if our spheres are exactly aligned. So to do that, you unscrew this little piece until the balance is centered, and this is resting. Then pull the one on the teeter-totter off, slide your second pole onto here, and at this particular point your centers would line up. So record this value as D0. As long as you're consistent in reading the top or the bottom scale, it doesn't matter. I used the top just because it was a little easier for me to draw on in the video. That'll be your D0. Then you will move that closer, and you can move that up a little bit or down. And as you get closer, the magnetic field strength increases, the interaction between those. And you're going to try to balance it. Move very slowly. This takes some time. If you need to, you can just stop it with your hand. And then if it keeps going, it's not balanced. Takes a little practice. And then when it does get balanced, using the motion of speed, when it is balanced, you would record this value up here. This is your scale reading. All right. So now what we're looking at is our second data collection table for part 2. So your scale reading, just what we said, this is what you measure. D is the scale reading minus D naught. Whatever you read from the scale, minus your initial value. F mag just comes from part 1. And then C star comes from your equation F equals C Q star. We're going to assume that our magnetic pole strengths are the same over D squared. So error analysis in this lab. Q star plus max deviation, you only have 9 trials, so no standard deviation in this case. Wouldn't be statistically significant. You'll get C star from part 2 with max deviation, and hopefully that'll overlap with the better way of finding C star, which is to use graphical analysis. If you graph force magnetic versus 1 over D squared, we're using 1 over D squared, so you get a very nice line. Again, make sure this is in meters, otherwise you get really odd numbers. And then the slope of this should be C times Q star squared. Q star squared again because we're assuming that the pole strengths are the exact same. So whole goal is to compare these. Basic wrap up, you're going to balance the beam using torque equations. You're going to compare your C from the graph and from the others. Physically what's going on, you have a moving current, or moving charge, sorry. You have a current which is moving charge. That creates magnetic field. More current, stronger magnetic field. Well, I hope that was helpful, and I will see you in lab.